Okay, so I'm going to go in this order of nomenclature, then isomers, and then finally I want to end off with crystal field theory. And so I'm trying to open up all of Chamberlain's slides on the side, but hopefully nomenclature is relatively straightforward in the sense that it's all open note. So if you forget like what a ligand name is, you can look it up. But there are still a few things that I want you to keep in mind. And I will go over that really quickly. So starting with nomenclature, you should always remember that the metal name changes depending on if it's a cation or an anion. So if it's a cation, that means it's a positive charge. Then you keep the name the same as the metal. So for example, if I were to just make up one on the spot, something like this, it would be something, something, something. Remember, ligands first. And then because it's a cation, I could say iron. However, if it's an anion, so let me use a different color. If I somehow did Fe, let's do something like this. Oops. My trick, well, because it's an anion, you know you have to change the name. And so in this case, it would be changed to ferrate. I don't know if it's the Latin or Greek or Roman or whatever, but you just have to change it. And several elements do this, and some don't. The main thing, though, with anions is you have to, well, I'll say change if necessary, but you also need to add 8, the suffix 8. And my easy trick to determining if you need to change the name or not is to look on the periodic table. So iron, using this example, the word iron is spelled like that, but on the periodic table, it's Fe. So if at any point the name spelled out in English doesn't match what it is abbreviated on the periodic table, that's how you know you need to change the name in the ion form. So some really big examples of this that you'll probably see a lot of are things like copper, silver, gold, lead. And so if you see any of these, I'm trying to think of any more off the top of my head. I know there's a fair amount, but if you see any of these, you need to change it to, well, Cu, Ag, Au, and Pb. And so obviously you can see here how copper doesn't have a U in it. And for the record, I write my U's like that. Sometimes it may be confusing with like a V or confused with a V, but I'll try to be clear. Copper doesn't have a U in it in the English spelling. So that means if it were in anion form, you would have to change it to cuprate. So this form, it now has the Cu, and we have to add the ATE. Silver would be argentate. Gold would be orate. And lead would be plumbate. And so this is just some things you need to keep in mind. and iron is ferrate, as I mentioned up there. You should remember that you need to go in alphabetical order when you're naming, and the point where you check for alphabetical order is with the ligand name. So what I mean by that is, if I go down a bit, if I had a complex, say, trying to come up with all these on the spot, let's use chromium. Let's use BR. I'll do BR2. BR2 CL. Why not? And if I were to just give this a charge, it'd be minus, I think. So for alphabetical order first, or for nomenclature in general, what I like to do is just break up all the pieces first. So what I mean by that is, that's one piece, that's one piece, and that's another piece. And so after this, we can start breaking it down and saying, okay, what are these ligands called? Well, the piece in yellow, it's water. And because it's water, I say it's aqua. There's 3 water, so I say tri aqua. And then we can go on to the second one, the green portion. That part is bromine. We change it to bromo. There's 2 of them. So I say it's di-bromo. And then finally, for the last portion, that's blue. That is chloro. And there's 1, but we don't really use mono, so you can just stick with chloro. And of course, we have to consider our metal. In this case, it's Cr, which is chromium. But chromium abbreviated as Cr. And chromium spelled out in English has an R in it and a C. So that means we don't need to do any fancy word changes here. So all we need to do, because it's an anion, we have to change it to chromate. Remember the ATE part. And so for this part now, to piece everything together, we look at the ligand name in terms for alphabetical order. So even though, like, if you were to consider only the first letter, T versus D versus C, you would think, oh, chlorine would come first or the chloro would come first. But we actually have to look at the ligand. So that's why we would start this name as triaqua dibromo chlorine. Oh yeah, I don't remember. It's chlorochromate. What am I saying? And then now comes the oxidation state. Don't forget your oxidation state. And just very quickly, water is 0. Bromine -1 each, right? And so is chlorine. Chlorine's also -1. So overall, this contributes -3. If we're looking at the entire complex, however, the overall complex is negatively charged. So in my head, I'm thinking something -3 or plus a -3 equals -1. So chromine must equal +2. And you would just throw it in there. The only other thing I would touch on for nomenclature is a very kind of obscure spelling thing. And what I mean by that are these two. NH3 is ammonia, but if it's in a ligand, or if it's a ligand, we change that to amine with 2 M's. En is ethylene diamine, but notice there's only 1 M. And so spelling does matter, because I do not want you to accidentally write an extra M and have points taken off, because I think they will take points off. Just double check your spelling for a lot of these things. Because again, this is open note. So if you are ever stuck, be sure you have that slide where she has all the ligands detailed with all the spellings too. I guess another small thing I could talk about. Move this here. Be on the lookout for when things have linkage isomerism, because the name of the ligand changes depending on how it's written. So if you see something purposely written like this, they didn't do it because they wanted to be fancy. They did it because it's actually bonded like this in the molecule. So for example, this top one would be nitrito, and the bottom one would be nitro. I know there's like an alternate spelling too. You can be like nitroto N and nitroto O. I think either is fine. I believe actually both of them are fine, but that's the one I remember. And so that's kind of what I really wanted to touch on for nomenclature, because honestly, the big portion of this chapter is on isomers and crystal field theory. So if I had to guess, you'd probably get like one question about nomenclature, but it'll be like part of a grand scheme of things where you have to, where she gives you like a formula, and then you have to write the name, and then you have to draw the isomers. So I would guess it's something, it'll be something like that. So going on to what I think a lot of people are here for are isomers. And I primarily want to focus on 2 types of isomers, more specifically geometric and optical isomers. I know she mentioned a few other ones like linkage isomers, which is kind of what these are. These are linkage isomers. There's also, I think, like coordination isomers, or the metal changes. But again, these are all kind of in the slides. So don't worry about needing to memorize all of them. I would think these are like the main ones. And okay, there's also ionization isomers, which are basically like the ions are switched with the ligand. So like if it was a salt, for example, the thing outside the brackets is switched with something inside the brackets. That's how you can think of it. But going on to isomers, one example you've probably seen is from your discussion manual or discussion worksheet, where you had to draw something like CO Cl2En2. You don't really need to worry about the counter ions. So for example, whoops, I did not mean to do that. For example, if there was, say that, you don't need to draw this at all. In fact, I would even advise you not to draw it. I think it was 2 plus or something. Let me get this down. So when we're talking about isomers, it kind of falls into 2 really big categories, where geometric and optical. Geometric, whenever I hear geometric isomers, I think of, that's a really bad C, cis-trans and FACMER. For cis and trans, you have 2 of a kind, and exactly 2 of a kind of a specific thing. FAC and MER, you have 3 of a kind, and exactly 3 of a kind. So if you had 4, if, for example, you had something like if you had something like this, the NH3 here, the amine, again, 2 M's, the amine here will not have cis-trans or FACMER. It's the water that will be cis or trans. And so, to break this down a bit further, cis equals same. And for an octahedral complex, same meaning kind of 90 degrees from each other. Trans, I think of across, like transcontinental. So that would be kind of 180 degrees from each other. FAC and MER are a little bit different, and I'm pretty sure your TA has mentioned it, if not Chamberlain has mentioned it in her lectures, but I'll still go over it. FAC, I think of a face. So they form sort of a triangle. They form a triangle or face of the octahedral. I guess it should be octahedron because it's the shape. MER, you can think of as meridian. And maybe you might recall hearing about in elementary school the equator and the prime meridian. The prime meridian is kind of like a vertical, or I think it's longitudinal line that goes through like Europe somewhere. But the key thing is that it's a line. So the meridian, you'll see a MER isomer if it forms a line, or T loosely. And so if we're drawing isomers of this thing right here, I see that we have 2 of a kind. And so that thing can probably exhibit geometric isomerism. I think it's easiest to think of the isomers in terms of the monodentate ligands. Monodentate, remember, meaning bites down on one spot, where mono means one and dentate meaning like teeth. You can think of dentate, dentist, they work with teeth. So I just like to think of it as biting down, or the cis trans referring to the monodentate. And so let's draw some isomers. I like to draw mine like this, but of course, if you like to draw yours a different way, be sure you don't confuse yourself. So if I'm drawing it this way and you draw it a different way, try your best to follow along. I don't like drawing it the other way because I've been doing it this way for quite a while now. So I'm just going to copy what we have to do. Let's do geometric isomers of, I'm just going to copy that one down here. Okay, so because we have two of a kind, we can have cis-trans isomerism. My advice to you all, and this is what really worked for me, is to utilize the square in the middle. And what I mean by that is, if I were, let me redraw this a bit better. Because this is an octahedral complex, you can try to imagine these four on the wedges and dashes as like on a square. And for me, it's really much simpler to rotate a square than it is to like manipulate something that's here and here. That's just personal preference. Because for me, I'm like, okay, if I need to rotate a square, all I'm doing is turning stuff like this. Okay. And that's just much easier for me to visualize in my head. So if I were to draw an isomer of this, if I start with the cis version, let's put the chlorines. Let's put the chlorines on the side here. Again, it doesn't really matter where you put it, but for me, it makes more sense to put it like that. So ethylene diamine, En, this brings up a good point where Dr. Chamberlain expects you to know how it's linked together, or how it binds to the, or chelates to the ligand. So ethylene diamine looks like this. It's also drawn in your slides. And I'm going to move this over. The bare minimum, and actually all Chamberlain really expects you to do, is to show the nitrogens binding onto it. And the way you know it's nitrogen is because nitrogen has a lone pair. And so any element that has like lone pairs can bind to it. And so if she does show you like a ligand that you've never seen before, and then she's like, what is the denticity of this? Just look for the lone pairs. And for this, I'll just put them, well, I know all the nitrogens go there. One thing you should remember though, is that bidentate ligands cannot attach trans. So I'm just going to make a bunch of copies of this, or just have this ready. So you cannot do something like that. So don't do something like that. you're going to lose a good chunk of your points if you do. Let me stick with green. And again, the reason is because it's not long enough to attach trans. And that applies to not only ethylene diamine, but your other bidentate ligand, oxalate. So what do you do? Well, let's just attach them as is, or the closest it can be. Something like that. So this is the cis configuration. And on the exam, when you are expected to kind of draw all your isomers or all the possible isomers for a compound or a transition metal complex, you should label each one. So I would say Cl cis for this one. And I'm just going to draw another one. Well, if we did Cl cis, what if we also did it trans, attached the chlorines to the molecule trans? Well, let's do that. For trans isomers, I like to put them, this is again personal preference, top and bottom. It's the easiest for me to see. And spoiler alert for later, it's really easy to find mirror planes and planes of symmetry for optical isomers if you draw it like this. And again, be sure you do not do that. You have to do something like this. And so you could label this Cl trans. This is kind of the first part. I don't think this is too confusing, like what the difference between cis and trans is. I think the big kind of question comes from what optical isomers are and how do you know if something has optical isomerism. So optical isomers, she may have said this definition in class, but the most basic or the one-liner definition is a molecule or complex with a non-super. All right, sorry about that. I have no idea what's going on with my voice. But let's kind of break down what this definition means. Non-superimposable, I think that word it's a big word. But one example I really like to demonstrate to students is to use your hands. And so if you can put your hands out in front of you, if you try to match up your fingers, so like palms facing forward, you try to match up your fingers, you'll find that even though the palms are facing the same way, your thumbs are on opposite sides. And I'm not even going to draw hands because I'm a terrible artist, but if you can do this right now, you'll see that you can't match up your hands. If you put your palms together, so like the thumbs are touching, the index, middle, ring finger, and pinky finger are all touching. Well, even though you matched up everything, your palms are facing different directions, right? One of your palms is facing up and one of your palms are facing down. So there's no way you can match up your left hand to your right hand. They are optical isomers. So one thing that you will hear a lot are terms like enantiomer, chiral, or even optically active. These all mean the same thing. they are non-superimposable, which means you can't match them up. You can't match up the mirror image to the original. So I'll also write that down. You cannot perfectly match up to the original, the mirror image to the original. And so what I'm going to do is I'm going to copy. I'm sorry for those who are taking notes on pen and paper. I'm going to take these two compounds from earlier, or these two that we drew earlier. So what I'm going to do, I'm going to call this section, I guess, testing for optical isomers. The strategy I recommend for pretty much everyone starting out is to draw the mirror image. So draw the mirror image. And try to rotate back to the original. And I think this is the part where now a lot of you are like, yes, this is where I'm confused. So I'll do my best here. And again, if at any point I say something that doesn't make sense or I do something that's really confusing, please let me know because this is super, super important. I can't really stress this part enough. So that thing right there, that blue line kind of represents the mirror plane. So if I were to put, I'm just going to copy this over here. And I'll just have more of these ready. Okay. So the way I do this, if the chlorines are on the very left side of the molecule, then if I reflect it or take the mirror image, it's going to become, or it's going to go to the very right side here. Let me, oops, move this. And then I can draw in all the nitrogens from the ethylene diamine and link them up. So let me get the color right. This one at the top connects with this one here. So it kind of does this thing. So the mirror of that would kind of do something like that, or those two would be linked together. Something like so. Which kind of leaves us with two left over, right? These two have to be linked together. And now comes the point where I can like blow a lot of people's minds. The first thing you should ask yourself every time you do this, ask yourself, are these the same? And just keep that answer at the back of your head because now we'll try to prove it if they are or not. This is kind of like why I leave the monodentate stuff in the center or in that square that I was talking about, that square here. What I will do, can I not paste? Okay, let me see. What I will do is I will now try to match up my mirror image to the original. And so I want to match up my chlorines. That's the easiest way to do it because if you try to match up your ethylene diamines or the bidentate stuff, that's spoiler alert, is where like it's probably where you're going to see some differences. So just try to match up your monodentate ligands. And to do this transformation, pretend that you are grabbing onto the center, like a top. Like you're holding the top from this line. And what I'm going to do is turn it 180 degrees. Whoops. And so, well, what's going to happen? The nitrogens are not going to move. The nitrogens at the top and the bottom are not going to move because I'm not spinning the stuff on this line. I'm spinning these four. Because I spun it 180 degrees, this chlorine is going to go 90, 180. So that chlorine I can label right here. Again, this chlorine, I'm rotating it 180 degrees, 90, 180. And you might be like, well, how did you know to rotate it 90 degrees? Or 180? Why didn't you rotate it 270 or 90? Well, I know that because if I rotate these two groups 180 degrees, they're going to end up on this side, which is where they were in my original. So chlorines are lined up because this one is going to go 90, 180. And what I can even draw, it's like little lines here. We're going around like a top or a merry-go-round, going in a circle. And now that kind of leaves us with nitrogen here, nitrogen here. The million-dollar question is, how are they linked up? Well, let's take it one step at a time. This nitrogen here, remember, it's linked, right? Because it's linked, this link does not break at any point. So they stay together. These two stay together. This nitrogen moves 90, 180, because we said everything is turning 180 degrees. So again, this nitrogen, 90, 180. So that means this nitrogen here and this nitrogen here are linked together. What's the best way I can do this? This might be a bit ugly, but it'll look something like that. So that kind of leaves us with one option, that these two nitrogens are linked together. And that was not my best drawing of it, but I hope you get the idea that, yeah, maybe I'll just do something like this. You might be like, why are you drawing it with a bend? Why don't you just draw it like a curve? Like that. You can draw it like a curve. The reason I'm drawing it like a bend is because ethylene diamine has some bends in it. So I'm just trying to be accurate there. I don't think she'll dock off points if you don't. If you just draw it like a curve, though. So here comes like, can you go over the nitrogen movement real quick again? Okay. So let's see, how should I do this? Do you agree, or going back to the chlorines, I'm moving the chlorines 180 degrees. So everything in this square has to move 180 degrees. The chlorines, I think a lot of people are able to see. The nitrogens, if I'm starting with this one here, this one is permanently attached to this nitrogen. There's kind of like a string attaching both of them together. So this string is always connecting these two together. This one's going to move 180 degrees. So I'm going to go 90. From here, I'm moving 90, 180. So in my rotated image, after rotation, after I rotate it 180 degrees, that nitrogen, which originally was here, is going to end up in this position. And remember how I said they were linked together? They don't break. They are still linked together here. All I did was move everything around like a merry-go-round 180 degrees. We can do the same analysis with this one here. This nitrogen in this corner is permanently linked to this one. So if this nitrogen moves 180 degrees, it's going to go 90, 180. And I arbitrarily chose this direction. You could have gone the other way. It's the same thing. Again, starting here. I originally said I'm rotating everything 180 degrees. So 90, 180. Because they're linked together, this kind of bond also moves along with it. And so because these two are always staying together, this one moves, the link follows. So that's why this one and this one are bonded together. Hopefully that made a little more sense. I know this is the moment where like a lot of people's minds are like, wow, I thought these were the same. But after doing the rotation, they're clearly different. And that is okay if you came to that conclusion. Like, it's okay to be wrong because you're not alone. I was in this position too. And this is my third year being a learning assistant. Every year I show them like an example like this, and like 99% of the time they say they're the same. I do the rotation and they're like, what did you just do? Because clearly they look the same, but now they don't. All I did was do a rotation and all of a sudden they don't look the same. But they're different. This one and our original are different. And so on an exam, you would label them optical isomers. You would have to draw both of them. And my advice to you all is to, if you see something with bidentate stuff, or if you have like a bunch of a bunch of different ligands, you should be suspicious because there's probably an optical isomer in there somewhere. It's really prominent if you have bidentate stuff. Okay, let's look at the trans isomer. The trans isomer, the reason why I drew it like this, well, let's do what we did above. I'm going to do the mirror image again. And so this one shouldn't be too hard because the chlorine at the top, the chlorine at the bottom. Oh, I think there's some lag. Yeah. So the top and the bottom are going to stay at the top and the bottom. These are called dashes because there's a bunch of lines there. That means it's pointing away from you into the page. These are called wedges. They're pointing out at you. So how this all kind of relates is that if you were to take a look at this thing in the bottom corner, and I'm going to zoom in on it, and I think there's a little bit of lag. So if at any point like I'm saying something and you're not seeing what I'm writing, just give it a little bit. If you can imagine this as an octahedral complex, this is what it looks like. And maybe I won't draw those dashed lines. But if you can imagine holding one of these in your hand, this part is what points out like at you. These two point out at you, and these two point away from you. It's our way of trying to show something as 3D. There was something I wanted to say. Oh yeah, this is how you can determine FAC. Remember how I was talking about a face of an octahedral, of an octahedron? This is probably much easier to see. Mer is where you form a T. So it's like, hey, do you remember what we were just talking about? Mer is like this, where it forms a T. You can think of it like that, or you can think of it as forming kind of a line. And I think a better example would be like this. You can draw a line that goes from one edge to the other. That would be Mer. And so this is just like another learning point. Going back to our complex. Well, the stuff that is on the far right is going to be reflected to the far left there. And same for the others, or for the other side. And I think you can probably see there's no tricks here like the previous one. These two are exactly identical. So always ask yourself, are they the same? This time, the answer is yes. But you should always draw the mirror image and think about it first before you get to before you say and conclude yes or no. Another way you could do this, and I don't recommend doing it this way because it can really trip up a lot of people who are just starting out doing this. If you can cut the molecule in half, if you can slice the molecule like that, then like if you find a plane of symmetry, then it is achiral. And so the trans isomer, we would say, well, we could say a bunch of things. We can say it is not optically active, or the trans isomer. It's not optically active. And it is achiral. And so if you do draw this on an exam, be sure you erase this, because if you draw both of them, the TAs might think that you did not know that these two were the same. They really only expect you to draw isomers that are unique. So you could do this analysis and say they are the same, but you should say that they are the same. Don't just leave this one here, you know? You want to be as clear as you can to the TAs who are grading your work. And so the quick way to do this, and like just looking at it, you can tell that it is achiral, is if you can find a mirror plane or a plane of symmetry. So like I can cut this molecule in half like this, and both halves would look the same. It's really tricky though, and this is why I don't recommend it to people, is because you could technically argue, you might say, oh, there's a plane there. But because you have bidentate ligands, it kind of changes a little bit. Think of it like a propeller. You know how if you were to look at like a wind turbine or like a propeller, these blades are not flat, right? They're kind of twisted, or I don't know if that's the best word, but they're kind of off at an angle. That's kind of what's happening here. These are also off at an angle. So it's harder to, you actually can't draw a line of symmetry there. And I highly recommend that you all check out Otterbein. I think Chamberlain sent the link somewhere, and I also sent the link in the resources tab. Basically, go there, play around with some molecules, drag it, turn it around, and practice seeing like what it's like in 3D. Because for me, showing you all, it might be like really easy. Like, oh yeah, just looking at me doing it is pretty easy. But when you get like hands-on practice with it, that'll really test like how well you know your stuff. And one thing I want to go over, going a bit up, these are all technically stereoisomers. These are all stereoisomers where you have one formula, but there's different ways of representing that formula, right? These two are clearly different, but the formula for both of them is the same. Both of these can be represented by the same formula. So that's what they mean by stereoisomer. When you have the other type of isomer, like I think she says like constitutional isomer or structural isomer. Structural isomers are dealing with linkage like linkage isomers kind of fall under that category, where the actual connectivity is different. So I'll write that down at the bottom here. I'll start a new page. So again, stereoisomer, the arrangement in space different, but the same formula. And the connectivity is the same. If you are dealing with structural isomers, you're going to see a whole lot of this for those that are taking OChem. If you have a structural isomer, that means your connectivity is different. So that's why if I were to kind of make sort of a tree diagram, like linkage isomers and what was the word? It was like the metal, where the metals switch. I can't believe I forgot the word, but the ionization isomer, the coordination isomer, that's what they are, I think. They kind of fall under that category, where a stereoisomer, geometric and optical. So it's kind of going back to how maybe in math or geometry, all squares are rectangles, but not all rectangles are squares. It's kind of like that, where there's like specificality, you know, some terms are more specific than others. I won't go into any more drawings. Maybe on Wednesday, I'll host like a shorter session where people can come with questions. If there are no questions, I'll do one of the problems from maybe the worksheet or even maybe one of the exam questions where we have to draw some of this, what time Wednesday, it would have to be probably like after 4. Ideally, it would be around the same time as what we are doing now. And don't worry, even though I said I was going to go from 5:30 to 6:30, I do want to finish off talking about crystal field theory. So I'm not going to leave you all hanging. For questions where you have to draw all the possible isomers of a compound or of a complex, I'll write this down here. Strategies for drawing all my strategy, and it's kind of generic, but work iteratively, as in go change a few things at a time. Change as little as possible between isomers. Little as possible. And my second big point is to keep the bidentate ligand in the square. The square meaning this here. That really worked out for me because I know that there's no like funky business. Because when we did stuff like this, whoops, I did not mean to erase that. When we did stuff like this, it did some really weird stuff where after you flipped it, right, you get something completely different. But if you keep them kind of in that plane, in that square in the middle, if you rotate them, even if you do any rotation, they're not going to do some kind of switcheroo on you. So if you keep them in the plane, keep them in the square, that will help you. They'll help you like work through your possible isomers. And between or with every single one, check for optical isomers. So some of them you can see right away maybe that there is a mirror plane, so you don't need to draw it. But if you're just starting out, I would recommend drawing the mirror plane every single time. Maybe like in your practice, get comfortable drawing the optical isomer, get comfortable drawing the mirror image and doing the rotation in your head so that when it comes time to it on the exam, you won't be struggling for time when you have to draw however many there are. And that's kind of a big thing too. She won't tell you how many there are. You'll have to work through step by step to see how many options you can come up with. So I guess kind of the last thing, if you think you reach the end, if you can't come up with any more, this is where you can kind of deviate from the steps that I mentioned above and draw what you can. So place them randomly in the sense. And see if they match any that you already drew. This is helpful because sometimes you do have to move that bidentate ligand out from that square. Sometimes it'll help, or you will get an isomer where like you'll see it if you put it at the top in there, for example. But I don't recommend you starting out to do that because if you try to rotate something that's here into the plane, into that square, it's pretty tricky. Okay, so I will continue onward. I know I've been talking for a while, but I will continue onward with crystal field theory because we are kind of nearing the end of all this transition metal stuff. Crystal field theory. Crystal field theory is all about the splitting of electrons and filling out that diagram, really. You may have recalled from Chem 2A where, like, remember seeing stuff like this, right? And maybe, depending on your professor, you may have even had to like do something like this, where you had to go fill in those electrons, kind of like so on and so forth. You probably got to a point, maybe, where you got to 3D and you just drew a whole line of 5. Crystal field theory says, wait a minute, those orbitals are not actually degenerate, meaning same energy. Some of these orbitals are higher energy than others. And we can use our complex here to talk about it. But first, you should try to recall the d orbitals. I don't really want to draw them all, simply because A, I'm not a good artist, and B, it might take some time. But I'll just go and describe them. dz squared, that one I will draw because it's pretty iconic. That one is the donut. It has a ring in the middle like this. dx squared minus y squared. Well, I guess I should have said all of these little subscripts tell you what axis the orbital is on. So z squared tells you it's on the z-axis. And then these kind of tell you that it has to deal with something with those x and y and z axes. dx squared minus y squared tells you it is on the x and y axes. So if I had to summarize, dz squared is the donut in the middle. dx squared minus y squared along x and y axes. Finally, these three. So I'll just say remainder, the remainder of them. They are between the axes. I am sorry. Who's calling? Okay. I'll be right back really. Okay, hopefully, I think my dad has to take a call. Hopefully that doesn't interrupt too much. But due to the fact that these three axes or these three orbitals are between so-and-so axis, that makes them lower in energy because the overlap isn't as great. Remember, electrons are negatively charged and they don't like to be next to each other if they can help it. So the more overlap there is, the higher energy there is. You're kind of pushing electrons together. So that is why if we were to split this, right, we can actually draw something like this, where we would label this dxy, dx squared minus y squared, and dz squared. That is why you see some gap here. And so if I scroll down a little bit, there are actually certain factors that can dictate how big that energy gap is. You'll see it labeled as delta O, delta meaning the difference in energy, and O meaning octahedral. And so you probably heard of something called the spectrochemical series. It's on your equation sheet, so you don't need to memorize it. But this tells you how strongly ligands interact with the center. With the metal. Okay, so if I were to just write some of them, greater than, I just know there's some like halogen here, so I'll just write, whoops, I'll just go something like that. Everything above water, I'll use a different color. Everything above water is considered strong, or a strong field ligand. It's strong because it interacts with the metal a lot and makes this energy, the split in energy, much bigger. And if you go on to take Chem 124, you'll hear a lot about that. Everything back here, though, is weak. So, including water. So, water and below is weak. That's how Chamberlain told us to remember it. Water and weak both start with W. And so, if you have a strong field ligand splits the energy more. I'm not going to label the orbitals, but you should do it on your exam, where like dxy, dyz, dxz, dz squared, dx squared minus y squared. I'll do it once. Actually, I already did it up there, so I won't do it again, but please do remember to do that on your exam. If you have a strong field ligand, yeah. Let's do the first case of a strong field ligand. If you have a strong field ligand, that's going to split your energy more. So it's going to make this gap bigger. And so how you can denote that is by saying delta O, I like to say large. That energy gap is large. And so I'm going to write this word here. And then for a weak field ligand, that means that this energy split is not very large, or you can say it's small. And so, well, this comes into play when we have to fill in these diagrams. Let's say, for example, let's say I had 6 electrons. For a strong field ligand, well, starting out, you would go 1, 2, 3, say D6. Because this energy gap is large, normally we would think to put an electron up here because electrons don't like to be paired up, right? But because this delta, this energy gap is large, it's too much of a difference in energy to go up there. So what we have to do is go down. 4, 5, 6. Only then could we, if we had 7 electrons, we could go up here. However, for the weak field ligand case, this gap is small. This gap is small, which means if we do 1, 2, 3, that means the electrons don't have to jump as far to get to the next energy level. So they can do that. They can split up. Only now I put down 5. The sixth one has to pair up. So it'll look like that. And so this is where high spin and low spin come into play. High spin and low spin kind of talk about how many unpaired electrons there are. Each electron, everything written like that, is plus 1/2. Has a spin of plus 1/2. Everything with a downwards pointing arrow is minus 1/2. So you can see how for a strong field ligand, because everything has to pair up first, they kind of all cancel out. Whereas with a weak field ligand, there's a lot of lone electrons, right? So that is what makes a strong field ligand also low spin. It's low spin because the overall, if you were to add up all these spins, it would be smaller than if you did it with a weak field ligand. So a weak field ligand is actually high spin. The way I remember this, a large splitting energy and low spin, they both start with L. So one thing that you should keep in mind is, going back a little bit, is how we came up with these two orbitals as being the highest energy. Because she might give you a complex or geometry that she hasn't talked about in class, but she would expect you to go through kind of the analysis we did. The more overlap there is, the more the higher energy it is. So you would label those accordingly. Does low spin or high spin absorb the longer wavelength? Good question. So let's get to that. In Chem 2A, there is a formula. Maybe you remember it, maybe you don't if you didn't like Chem 2A and blocked it out from your memory. There is a formula, E equals hc over lambda, where the energy and wavelength are inversely related. So the bigger your energy, the smaller the wavelength. So if you have a large delta, that means the electrons have to jump up, or they need more energy to jump up to the higher level. So because of that, the strong field ligands absorb the lower wavelength or smaller wavelength. And so the opposite is true for the weak field ligands. They absorb larger wavelengths because this energy gap to promote the energy needed to promote an electron isn't as big. And so you should also remember from Chem 2A the difference between the term paramagnetic and diamagnetic. And so paramagnetic means you have unpaired electrons, and diamagnetic means you have everything paired up. And there's actually no correlation between like strong field being always, or in this case, being diamagnetic. There's no correlation there. You have to draw it out every time because it's different. The only correlation there is this stuff here. And so, kind of reaching the end, two more things. If you have a tetrahedral complex, delta T, we use T for tetrahedral. Tetrahedral has it flipped. And she goes over this in lecture, but basically the orbitals don't really have great overlap because remember in tetrahedral, everything is, or if you remember the angles from Chem 2A, the angles here are 109.5. Whereas the angles in octahedral are all 90. Yeah, so the stuff we just did were octahedral because that's why I labeled it O, delta O, O for octahedral. Now I'm briefly just going to talk about tetrahedral. I'm denoting it by T here. With tetrahedral, your orbitals are labeled a bit differently. Well, not too differently. It's just these are the higher energy ones, and these are the lower. And so with a tetrahedral complex, this energy gap is small. And so comes the saying, or comes like the fact from her notes, tetrahedral is always high spin. Right? Because we said if the energy gap is small, it's high spin. And so if you were to fill out your electrons here, you would go 1, 2, and then you can jump up. Finally, I'm going to talk about colors. And I know some of you may have other things to do. So if you need to go, please do so. If we're talking about colors, I would be super extra and do this. There will always be a color wheel. I don't even know if you can see that yellow. There will always be a color wheel provided on your exam, so you don't need to memorize it. But basically, the color that you absorb is not the color you see. The color you absorb a certain color, but you reflect what's opposite to you on the color wheel. So if you absorb red, then you reflect or appear green. If you absorb orange, then you appear blue. Going on yellow, violet, green, orange, blue, or not green, orange. Green is red, sorry. Blue is orange. And violet is yellow. And so you have to be a bit careful here because be sure you are clear with what information they give you. Are they saying the color it appears, or are they saying the color it absorbs? And you should also maybe try to remember that this is high energy. If you absorb violet light is the highest energy color, and red is low energy. So that's why if you see if I zoom out a bit, if you see a complex with a strong field ligand, it's probably going to absorb violet light or high energy colors, which means it's going to appear red, orange, or yellow. And there's one situation I didn't really cover and I should have. You might have a complex where you have both strong and weak field ligands. So if you have, I'm going to go down here. If you have both strong and a weak field, you might be like, well, what do I do? I'm kind of stuck in the middle. If you have both strong and weak field, so same, I'll say minus, then you use the large splitting energy. And that's pretty much it. We did a whole lot. I covered a good amount, actually, maybe even the whole chapter in an hour and a half.